Well, thank you everyone for turning up to the talk. I was dubious about how many people would come to a talk at a conference about a paper. Just to get an idea of who you are, who here has actually read the Dynamo paper? Good chunk. Who here is using a Dynamo-inspired system? So DynamoDB from Amazon or Cassandra or Riak? Nope, just interested. Okay. So we're going to be going through the paper in quite an abstract way, but I'm going to refer to features in Riak and features in Apache Cassandra as I go through, because the paper itself, obviously we don't know the implementation. That's something internal inside Amazon. What we do know is that some databases came out of it, and they made different choices based on the proposals in the paper. So I will try and refer to, say, database X, say Cassandra does this, Riak does this, etc. Little introduction just so you know who I am and why I'm talking about this stuff. So I work as a freelance software engineer and architect in London. I generally work at clients that have very large operational systems. So they're normally using databases that are either at least spread across many servers, but are normally across many different data centers. I also work for a consultancy called The Last Pickle. They're like a specialist big data consultancy. They do a lot of work with Apache Cassandra. So we're going to go a little bit of an introduction into just how we scale existing databases. The current production system I look after uses a combination of Cassandra, which is a Dynamo-inspired database. It also uses MySQL, and it uses CP-style stores like etcd and Zookeeper. So I'll refer to those as we go through. The reason I decided to do this talk is we were doing a reading group. I was trying to encourage people to read more papers, and we were reading Dynamo, and then I thought it'd be a really good idea to maybe do this at a conference talk. But one of the main reasons we were doing a reading group, one of the main reasons I wanted to do this talk is I think there are so many different systems out there now, different database systems. If you take from, say, 2005 onwards, and you look at the number of Apache projects that have gone up and how many of them are databases, it's really quite crazy. And it's near impossible as an active developer to keep up with all of the different systems that seem to be coming out, database X, database Y every new week. But if we go and learn some things which are maybe 15, 20 years old, and we understand a little bit about how those systems are designed, so we say, should we use etcd, should we use console, should we use Zookeeper? If we understand a bit of the theory behind it, we can very quickly get a good idea of what that system is capable of. If a system has a master in its architecture and it's a database, you know that high levels of consistency can be relatively cheap, because all of the writes go through the same place, so it's all on one server. But you inherently also know that you're going to have some downtime. So if you need a 100% available system, and it has a master in it, it's probably not going to be possible. As soon as you need to patch the operating system, as soon as that server goes down, there's going to be a failover mechanism, and we're going to have some downtime. And without really researching, a database or a queuing system, just knowing that can give you an idea of its capabilities. As someone who visits a lot of companies, I often get this question. Which NoSQL database should I use? So the first thing I respond to that is a bit like, why are you trying to use a NoSQL database? NoSQL databases, they're around 2-3% of the market. I would much rather use MySQL or Postgres than most of these modern databases. They're much more reliable, they're better tested. The follow-up to that question is normally this. Should I use Mongo or Cassandra? I can only assume that question comes out because they're the top two on DB Engines, the website. And in reality, once you've done a little bit of research into, say, Mongo or Cassandra, from the technical point of view, I don't think you would ever use both of them for the same problem. They have different system architectures, they have different data modeling, they have different failure ways, they offer different forms of consistency. Like for a particular problem, if you just drive it down to the requirements, I don't think you would ever, actually seriously consider using them. They're for very different problems. So the first thing I encourage people to do when they're contemplating using a new technology is look into it a bit. And I think there are two main areas of a database technology that you can look into. The first is how you're going to do your data modeling. Right, so we start off with extremely simple things like key value stores all the way up to brilliant graph databases in SQL. The next thing is the system architecture. What are its actual components? Is it made up of 6 different processes, a sharding server, a master, and a replica, etc.? There's all these different things. Or is it a peer-to-peer based system like Dynamo is? And they're the first things I try to learn out about. So we can start at the very basic. We can have key value stores. And the Dynamo paper describes a key value store. But a lot of the systems that have been built from it are actually different. They offer you more flexible data modeling, which affect your application design. On top of that, we've got document stores. So document stores really are key value stores, apart from the database understands a bit about the value. So it's very typical to use JSON for a key value store. So eventually those type of databases can start to offer functionality that looks into your value, looks in and say offers you an index on a particular JSON field. Though distributed indexes generally don't perform very well. Then we've got column family. So a column family store is again, it's a better version of a key value store. You've got a key, but then the value is separated into different columns, which the database is aware of, and you can update them independently. That gives you a huge amount of flexibility and will let you dictate what type of consistency you can get out of that system. And then right at the top, we've got the brilliant ones, things like full SQL and graph. We don't want to give these away. If our data set fits on a single server, and ideally fits inside RAM, so as long as it's in the hundreds of gigabytes, you can get complete ad hoc querying on normalized data, and you should probably do that. The types of systems that we're going to solve with Dynamo-based databases actually are dealing with a much greater data set across a much larger scale. So trying to do full SQL on top of a distributed database spread across 10, 20, 30 servers is not a good idea. You'll end up having to go to all of the servers. System architecture, though, is what we're mainly going to talk about when looking at the Dynamo paper. Because even though it describes a key value store, the majority of the paper is about how to design the system, how the components interact, where do we place the data, how do we query the data. But we'll start off with a single server and we'll build it up. If you're using existing databases, lots of your MySQLs, your Oracles, etc., the first thing you do when you move from a single server is to go into something called master-slave. So even though your writes go through the same place, you can start to read from read replicas, which is great. You get to scale the reads. But if we look at it, that's instantly going to tell us that we have some downtime, and we could have stale reads depending on the replication to the slaves. Then we've got one of the scariest things I've ever come across, which is a master-master transactional database. I always fail miserably at trying to make these things, these things scale, etc. You end up having commits that go across data centers, and you end up essentially in live lock where each one keeps on trying to, roll back each other's commit. But what we're going to talk about in Dynamo is a purely P2P, peer-to-peer system. And that's great. We're going to get some huge benefits from that. Sometimes mandatory requirements on scale and fault tolerance are going to mean that we can only use a peer-to-peer based database. But we're really going to have to think about consistency. And we're really going to have to think about conflicts. And conflicts are going to be our new thing that we model around. Rather than have the database be our ball of consistency that can guarantee that we don't overwrite a previous value if we didn't mean to, we're going to have to start thinking about that at the application level. So let's start with a single node. How do we get from a single node to a database that looks like one described in the Dynamo paper? So I like single node databases. They are fantastic. If you can fit your data on a single server, you can probably query it ad hocly, because everything can be pulled into memory and things are good. But at some point, we want to scale it. And the last system I worked on from scratch, we were doing that. We were building bigger and bigger servers to run our favorite Oracle database on. So we were just spending money. That's fine. But we're here to learn about the Dynamo paper. So we're going to be learning about horizontal scaling. And there's horizontal scaling in existing databases that normally involves, sharding master-slave setups. But that's not what we're going to talk about today. We're going to talk about peer-to-peer. Every single server inside our database cluster can handle any read or write. So how does that work? We're not going to fully duplicate our data because that's not going to scale. We want to be able to basically have a sharding style mechanism built in. And if we're going to talk about this and we're going to talk about availability, unfortunately I will mention the CAP theorem, which isn't the best for describing real systems. But I will go through it because it's a good starting point to discuss a database. And then you can actually talk about the actual behaviors of the database system, right? Because who here has actually read about the CAP theorem, etc.? So about half. So we'll just dive through it. It's used a lot in database marketing literature, normally incorrectly. So in CAP theorem, it's basically saying for a distributed system, and let's just assume we're only talking about a distributed database. It's normally, it refers to a register. We get to choose between two of three different things. And those things are consistency. But it's a specific type of consistency this theorem is talking about. It's talking about linearizable consistency. So that is a defined order of events, and you can never read stale data. Not many databases give you that. The next thing we're going to talk about is availability. And it is full availability. So if we have a distributed database spread across all of our data centers in a glorious way, regardless of what happens, the nodes, the servers that are still functioning will always service your request. They won't say, no, I can't do that. They're always going to say, yes, I will do this read or write for you. Again, don't know many databases that do that. And finally is partition tolerance. And it's generally expected that if you're running on more than one server, you have to be partition tolerant. If you want to understand what happens when systems aren't partition tolerant, take RabbitMQ, put a partition in between it, and then have it merge after you've written many gigabytes, and it just throws away half of the data. Don't get me wrong, though, that is documented, and you can turn it off, etc., but it's quite interesting. The worst thing that can happen, I think, in a database system or a queuing system is that it's built expecting a master, but then it ends up with two. Bad things happen then. A theory, or just a blog post really, which I actually prefer when discussing real-life systems, is a funnily one called PAC-ELC. And this basically says, when there are partitions, right? When there are partitions, we get to choose between availability or consistency. And for me, this is intuitive. So if I have 3 database servers, stick a partition in between so they can't communicate anymore, do I continue to service requests on all 3 nodes? If I start to service them on the single node by itself, it could easily be processing the same writes which are on the other 2. All right? The alternative is to say, nope, I'm not going to service requests, or I'm going to service the requests on the majority side. And neither of that's available in the cap sense. But most of the time, I only really care about latency. So in a Dynamo system, it's a peerless system, which means that I'm going to have n replicas for a piece of data. So I want to store my name in that, name equals Chris. I need to get it to 3 nodes. Now, I can either wait for it to be fully replicated and incur a lot of latency, or I can just say fire and forget. And that's generally what I'm trading between. But in any Dynamo system, you're not really talking about linearizable consistency. We're talking about much lower ones. And before we move on to explicitly Dynamo, if we have a look at our existing architectures of most technologies I use in production today. So our classical master-slave, where we have all of our writes going through the same server. And we either asynchronously, or if you're in MySQL sense, which I'm a big user of, semi-synchronously replicate to some other servers. So all writes go through here, but then they're sent out here. Now, this replication is asynchronous. If we want to be partition tolerant, asynchronous is great. Because if this is cut off, if these can't communicate with each other, then we still remain available here. We still won't accept reads or writes here, of course. The next thing to normally do is to start redirecting reads to these. And at that point, we have eventual consistency, right? We're asynchronously replicating, and then but we can read here. So imagine you write coming into here, and then a read comes in, then we might not see our write. We've given up some consistency to improve performance. Of course, when we want to come to scale writes in this traditional architecture, we get into the wonderful joy of sharding. Now, depending on the system you're using, sharding might actually be a supported mechanism. So the actual database itself understands this. And this is where we're essentially running multiple masters, and we're partitioning our data between different areas. So all customers from A to C might be here, C to X might be here, or whatever. Now, is this partition tolerant? Well, it depends, right? If we don't try and do reads that involve data on both sides, and we've got asynchronous replication, it's pretty partition tolerant. Is it available? Well, absolutely not, right? We can see clearly that this isn't available in any way. If we want to read, Bob, and he's in this shard, we can't go to any of these nodes. If we want to write Bob, we can only go to this node. So how can we do things differently? What does the Dynamo paper say? Well, we're going to describe it all, but essentially it's going to be peer-to-peer. We're going to be able to send reads and writes to any node inside the cluster, and we may or may not be available depending on the options you set when you read or write the data. So let's see how that happens. So we'll start off with consistent hashing. So if we're going to have our database be spread across many servers, we need a way to spread the data to deterministically know where to go and get, the record for Chris. And this is done with consistent hashing. So if you take a key value store, the simplest of data modeling, what you do is you hash the key, say with MD5, murmur3, and it's going to give you a big number, 128-bit number. And then for each of our nodes in the cluster, each of our servers that we're giving to our database, they can own a range of this hash function. So we could say that node B owns range 0 to 249. Now, I couldn't fit the numbers for 128-bit numbers on this slide, so I pretended that it only goes between 0 and 999. But in reality, what we can do here is that any node in the cluster can hash your key and work out where the data is. More importantly, the Dynamo paper discusses that you can either do this on a different node, so even if we wanted to read data that lived on node B because the key hashed to 0 to 249, we could either go to node B, we can build that logic into the client, and most real Dynamo-based systems do that. They constantly get updated about the topology of your database, and they actually do the hashing on the client side and go directly into the database where it needs to go. But that's not mandatory. We can actually go to node C, and it will just internally reroute our request. So let's see that in practice with some fancy animation and balls. So imagine we have a bit of green data. Imagine we hash that, and we found out that it lives on node A. So the client's quite clever, it can go directly to node A. The other part of Dynamo is to be an always-on writable database. So what happens if node A is down? Can we continue to write? Well, yes, because a piece of data doesn't live on a single node in a Dynamo system. It lives on multiple nodes, and that is generally configurable. We're going to call that N. So let's say we did actually write it to A. It's A's responsibility for coordinating that request to also send it to node B and to node C. So the client doesn't need to do this. Whoever receives the write request does. Now let's say we pick up a different piece of data. This is the yellow data. That might actually hash to node B, which means that we're going to copy it, we're going to walk the ring and put it on node C and node D as well. If you actually look at real implementations of the Dynamo paper, like, say, Cassandra, they have fancier replication strategies in this. There's one called the network topology replication strategy. And it does walk the ring just like this until it gets your desired number of replicas, but it avoids nodes that live on the same rack in your data center. So that means you can start to handle full racks going down, full partitions between racks, etc. But different Dynamo systems do this differently. One thing, if you go and look at some other databases that aren't so Dynamo-inspired, is they can use the consistent hashing, but they don't necessarily need to be a masterless system. In a way, I believe Couchbase works like this. So even though it replicates the data and it handles that internally where the data is located, you can actually only go to a particular node to read and write the data. And this has benefits and it has downsides. It means that when you knock down a node of something like Couchbase, some of your data will be unavailable. Like you won't be able to write it, which could be the choice that you want. But you can read it from other nodes. But we're going to keep on the Dynamo stint, so that's where essentially every single node is equal. So remember, we hashed A to the green. We hashed the green to A, but that doesn't mean it's a special node. That node does not need to be up. It might be first in the list of popular places to go, but if that node's down, we can just either write or read it to node B and C. So how do we use that as an application developer? So the terminology differs between the implementations, but I'll use the one from the original paper. So when we actually send in a write request, let's say we're trying to write green. So our end goal is to get it to node A, node B, and node C. We have S equals 4, and this basically means we've got 4 servers. N equals 3, which means that we want to replicate it 3 times. So when we specify a write number, we're not affecting how durable the data is. We're not saying only write it to one server this time. What we're saying is, the node I'm communicating with, node D, I want acknowledgements from at least one server. So the write is going to go out to all of them, regardless of what write consistency that we ask for. However, we only need to wait until node A says yes, or node B, or node C. It doesn't matter which one. And this is the typical trade-off between latency and consistency. If we ask for 1, the query is going to come back really quickly. If we ask for 2, or we ask for 3, then we're going to be waiting for the slowest replica. We're going to have occurred latency, but we know if we come back, like as in the same client comes back, we're definitely going to read this data unless it's been overwritten subsequently. But if we lower our consistency to reduce latency, Like let's say that we knock it down to 2, but then we do a read of 1. Now the read number is very similar, except we don't need to go to all 3 nodes. The read number is saying how many nodes should I consult? Like if there's 3 replicas, should I check all 3 of them and get the most up-to-date value, or should I just go to 1 or 2? Now if we start to write data at 2 and read data at 1, when we have 3 replicas, are we guaranteed to get the latest data? Well, no, because D could have got acknowledgements from A and B, and we could have gone back and carried on with our application logic. The other client over here could have gone to node C. No guarantee, this is eventual consistency. What we can do, though, is make sure our read and write numbers overlap. So with a replication, so with n equal to 3, we can specify both read and write to 2. And that means essentially that we're guaranteed to have 1 overlap. What's really important to note, though, is this is not linearizable consistency. Even if you read the documentation of certain Dynamo implementations, definitely not linearizable. We don't know which order these happened in, the read and the write, etc. And if we've got multiple writes going on at the same time, then we don't know which order they actually happened. The next thing that Dynamo does is try to improve the write availability even more with something called sloppy, which is a really cool name for a computer science thing. So imagine we're trying to write this data again. We know that node D is coordinating the request. That's the one we've gone into. We would like at least 2 responses before we continue on with our application. What happens if these 2 nodes are down? Can we reach 2? Well, we can't, right? Node A is up. Node D is not on the list of replicas for this piece of data. Now, if we look at certain implementations of Dynamo, like Cassandra, this would definitely fail. There's no way to make this pass in Cassandra. If we look at, say, the Dynamo paper or any system that implements these sloppy quorums, what it essentially does is say, I'd really like to put it on node A, B, and C, but B and C are not having a good day. So why don't I just keep walking and put it on D? And this is temporary. We're basically increasing the size of the node, like the number of nodes that can look after this data, while node B and C are down. Right, but node D kind of knows that this is not what he's meant to do. His goal in life was not to look after the green data. So he's not going to keep it forever. Otherwise, we could eventually put the data on every single node if we had the certain, sorts of failures that go around in a circle. So node D keeps that in a separate area. And what it does is he waits for node D, so node B and C, to come back up, and then he'll send it to them. This is called a hinted handoff. Cassandra has a similar thing, but it's not this. It's not what was described in the Dynamo paper. Cassandra actually can't let you reach consistency levels unless the original replicas are up. But what it will let you do is specify a consistency level of any, which means that the coordinator can just keep hold of it until the nodes come back up. But that is a Cassandra-specific feature, not what was said in the original Dynamo paper. So everything seems good so far, right? We've increased our availability. We've increased our fault tolerance. For the Dynamo systems I've run in production, I would happily walk into our data center and turn off any database server. I've even done it. I've turned off entire racks. I'm completely happy to do that without affecting uptime. I don't know if other databases with different architectures will allow me to do this. But there's a downside. The downside is the complexity of conflicts, right? Because we do not have the ability to lock and we do not have a defined order of events in our system, we are going to have conflicts. What do I mean by this? So let's go back to our friend, the green data. So the green data needs to live on node A, B, and C. So that's got key CH Batey, Chris say. What happens if another client also decides he wishes to update the same key? But he doesn't go to node A. He goes to node B. How do we deal with this? If we're inside a relational database and we had the consistency level tuned up, then this transaction would have to wait until this one was finished and it would definitely see the results. In a Dynamo-based system, they can just go at it. You can just keep writing and writing and writing, and the conflicts are resolved on read. So let's see how that works, because it's a very easy way to lose data. So if we're in a key value store, this is kind of scary, because a key value store has to replace the entire value. So if you want to update one field in a key value store, you have to read it, deserialize it, update it, send it back. If you accidentally lose an update, one of the values, you're going to lose all of it. You're going to lose the entire value. column family stores. So this is where the database is actually aware that the fact that for a particular key, we've actually got lots of separate columns that can be updated individually. Now, one distinction is between the Dynamo paper and DynamoDB in Amazon. So the service that you can actually buy and use, it's not Dynamo. It's another database inspired by it. Now, the Dynamo paper talks about key value. The DynamoDB database and the Cassandra database, they actually look much more like column families. Whereas RIAC, for instance, is a key value store, but it has CRDTs that are pretty awesome. So let's see how we can resolve this conflict. We'll do it for both a key value store, we'll do it for a column family store, and see what on earth can go wrong. So the first tactic we can use is wall clock time. Now, what could go wrong in a distributed system if we use wall clock time? Whose servers are in sync all of the time? Well, they're not. But I'm actually going to do an example that assumes they are in sync, and we can still lose data. This is a scheme called last write wins, and in general, it's not a good idea. So imagine you have this. So you've got, I'm trying to write CH Batey, his name is Chris, his age is 25, which is a complete lie, and his email is blah@blah.com. And we're going to write it at time 1. So we can assume this is milliseconds since epoch. So we're in 1970. We've gone back in time. Node B, so let's say a client comes in and he reads that data and he says, Chris has been lying about his age. Let's bump it up a little bit. I'm still not 26, I'm much older than that, but I'll lie again. Now he can, because this is a key value store, we have to overwrite the entire thing. And we've said the name is Chris, we've updated the age, and we've said the email is blah@blah.com. This hits the server at timestamp 2, so this guy would definitely win if we were trying to read this data. We can kind of garbage collect this away, this is out of date. Now at the same time, so imagine an example from a couple of slides back where we're trying to write, two people are trying to write the same key. Now imagine it, we come in at time 3, we actually read A's value, because these two are happening concurrently, and we want to change the email. So I've changed the email from blah@blah.com to wah@wah.com. But because we read it from client A's value, we've put in age 25. Because this is a key value store, we've had to update the entire thing. So what has happened? It keeps me young, but it's also data loss. This is why last write wins is terrible in distributed systems. So what are the alternatives? We can improve this in many different ways, and we'll go through them. So if we look at the column family stores rather than the key value stores that implement the Dynamo paper, the real difference is that for a particular key, each column is its own entity. You can update them individually. If you look at the implementation of some of these systems, they have their own timestamp. So imagine we write the first one. But this time, we've actually got a timestamp for every single column. When we want to update the age, we do not need to update the entire value. So we can just send in age equals 26 with timestamp 2 this time. When the other client comes in and says, I'd like to update the email, it's time 3 now, or it could even be time 2, and he wants to update only the email. And when we read this, then we can pick bits from both. So we can say CH Batey, we get the name from the original one, we get the age from the middle one, and we get the email from the last one. So column family stores give us more flexibility if we're not concurrently updating the same column. If we're updating the same column, we're back at square one. So it's not the end of the story. So what alternatives have we got to last write wins? So the Dynamo paper discusses how Amazon did it, and they had 2 options. It was a key value store, so they had last write wins that they used for data which they didn't mind losing. So it's things like session state, etc. But then for things they really didn't want to lose updates for, the example used is shopping baskets, they use vector clocks. So vector clocks are very old. What they do essentially is allow you to detect that you've conflicted with someone. So let's see an example. So we're going back to a key value store because they're more important for key value stores. So if client A wants to update this data, he sends it into the database, and the database might say, that's the first time A's done something. I'm going to give him the number 1. Make sense? When node B comes to read that data and rewrite it, he can resend in the same vector clock. So when you read data in RIAC with vector clocks turned on, it gives you the vector clock and you send it back in. So when we update the age to 26, we send it in, and we add our own value, or the server will add their own value. So we know that A has modified it once, and B has not modified it once. When node C comes to update it, so when client C comes in, remember he's updating the email, but he's doing it having read A's value. He hasn't seen this one. So what's he going to do? Well, the vector clock becomes A1 because it comes from here, and then he only adds C1. He's never seen B1. Now, with this, we can actually work out that these two have conflicted. Right? When we write this one, we know we've never encountered this one in that write path. And the way vector clocks work is, you know something is descendant from another one if everything is present in the vector clock and the number is greater. So in this one, and if you're not in there, it's assumed to be 0. So B definitely descends from A, because A is greater than or equal to 1, and B is less than or equal to I don't exist, so 0. So this is descending. But these guys, in distributed system speak, these are concurrent. We don't know which order it happens. So what can a database do about this? Well, this is your data, so you need to decide what to do. What vector clocks do inside data stores is give you the option to be notified as an application developer that a conflict has occurred. So when someone comes and reads this value, what do they get? Well, they get both. It's up to us as application developers to merge this. How you merge it is completely up to you. So when D reads this, the database is actually going to give him both values, and the vector clock becomes, and then he does the merging, and then we get a vector clock which includes A1s, B1s, C1, and D because he did the merging. And we're back into good ways. If you have a data structure which can be automatically merged, you get into the world of CRDTs. So that's when the database can do it itself. And a classic example of this are things like sets. You know how to merge a set, you know how to merge a counter. We don't really know how to merge this. It's up to the application developer. Maybe we say, someone can't really get younger, so I'm going to take this one. And we know we can probably get the value for A1, so we can realize, hey, the emails have been updated, so we're going to take this one. What are the downsides of using vector clocks in databases? Well, I had 3 clients, and I've got 4 clients now, and look how big it's getting. Vector clocks very quickly get bigger than the actual data that you're going to store. They also require you to do a read before every write. So what ideally I want in a system is a mechanism that provides both. Last write wins without reads before writes for the high performance where I can lose data, I can lose parts updates. When I want more consistency, I want something with vector clocks. We don't stop there, though, with Dynamo-based systems. There are other ways that we can model around conflicts. We can make sure they don't exist. Now, this is only applicable for systems that have been built in the column family era, not key value. So we can basically try and model our data immutably. This is extremely common in Cassandra. The applications I'm currently running in production, they virtually all model their data this way. And it's stolen from event sourcing, and there's often using a framework which I help contribute to called ACA persistence. And how does that work? So let's say we're going to store a bank balance. Are we going to store it as, with last write wins, with the value minus 240? Apparently I don't have any money. We know this is a bad idea. If we read and then update this to a new value, we are going to lose data. So instead of storing an absolute value, instead of having a distributed mutable variable, which just sounds like a bad idea, what we're going to do is have an immutable log. So here, we're actually going to store the operations. So we're going to say it went -5, then +2, and then +20, etc. We never update the same column ever in our database. And typically what we include as part of the key here is a unique identifier. So we can have as many as we want, so we don't need to somehow coordinate that this is 1, 2, and 3. This really only works, though, if the order of the updates don't matter. And generally, you want things to be idempotent. This generally slows down, though, because eventually what we have to do to actually work out the balance is read all of these values. We need to read them all and then add them up, etc. So this is normally combined with snapshotting. So once a night or once every 6 hours or something, we'll actually read all of these and build a snapshot. We know that the state after these have been read is 17. Once we've done the snapshot, we can then start adding more operations, etc. And that's basically what ACA persistence does. One more thing to discuss before we hit the end. We've gone through consistent hashing. So Dynamo-based databases use consistent hashing to place the data. We've gone through replication. Now, there are a number of reasons for replication. It's fault tolerance and availability. So if we want to be able to read our data, we want multiple copies, etc. We've talked about the joys of conflicts, which are pretty much the complexity that you're adding by using a system like a Dynamo-based system. But I'm going to go for Dynamo++. So most of the databases that have been built based off the Dynamo paper are starting to include features that you would not expect, features that weren't mentioned in the Dynamo paper. So what I've done over numerous years is always to have something like Apache Cassandra running, but then also have something like Zookeeper or something like MySQL. And the reason is I have certain operations in my application which just can't handle any of the above. Any of the other conflict strategies. An example would be, let's say I have a finite resource. I've got cinema tickets, or I've got theater tickets. I have 300 of them. And people get really mad if you sell them a ticket and then you actually say, sorry, it's full. Virtually every booking system in the world will do that, though. They're all eventually consistent. Even airlines do it. It drives me nuts. But essentially, we don't want to do that. So let's say we've got 300 tickets. None of those things that I've told you, vector clocks, event sourcing, like immutable data modeling, none of that would allow you to not sell more than 300 tickets. Because think about it. Let's say you've got 299 tickets sold. You would both read it, and then you would both write it to 300, and then a vector clock would tell you it's conflicted. But you've already sold the ticket. So that's not good. So a lot of these systems, I would then move on to using something like a relational database, something which is going to offer a functionality like compare and set. And compare and set basically says, I want to write it to 300 if and only if it's 299. And if we get this example again, where two people are trying to write it, the database system itself should be able to say no to one of them. And that is not how Dynamo systems work. They're just like write, and then worry about it on read. But what I see now is that things like RAC and Cassandra, etc., they're offering functionality where, let's say you have 3 replicas for a piece of data. Rather than appending on, keep appending, there's a write operation which allows all 3 of them stop what they're doing briefly, have a little chat, and agree on the next value. This is considerably slower, right? It's going to be much slower than any other event. And it doesn't work very well in any of these systems when it's contended. Because what happens in these algorithms which work across the 3 nodes is if there's 2 conflicting ones, they need to do something. One needs to fail, or one needs to wait, or one needs to retry, or one needs to take over the value from the other one. But they are getting there. I don't think I'm removing my consistent store yet, but I would rather a database offer me both. And there's a bunch of algorithms, and this is my joke at a picture. So the major algorithm is PAC-ELC, which is just a consensus algorithm for distributed actors agreeing on something. And then you can build on top of this to constantly update, say, a log structure. Another one is Raft, which is a much simpler version of PAC-ELC, certainly from a conceptual reading point of view. And the last one, which has got a different use case, which I don't think has appeared in any of the Dynamo databases yet, is ramp. So he's walking down a ramp. That's my version of a joke. That is a different piece of functionality. So PAC-ELC and Raft, they are for distributed consensus. So like, let's say we want to build a compare and set operation, which means I can say, set it to 300 if it's 299, set it to 301 if it's 300, which means I do get this defined linear order of events. What ramp does, it's called read atomic multipartition. So this essentially says, in all of the Dynamo systems, they're all based off a key, right? Even if they're column family or their value or their whatever, right? But what you can't do in any of them is make an atomic update across keys. Just doesn't work. Whereas ramp is a protocol for basically working that out. And it's doing it simplistically from, if I read this key, it's actually storing some metadata to say it was stored with this other key, you better go and read that value as well and return both. All of these move away from Dynamo's actual principles, but they mean that you don't have to run multiple databases in production. So to summarize, Dynamo is a pretty interesting, approachable paper. I definitely suggest you all go and read it. And it's a domain that we really understand. It's a basket service in Amazon. One of the great vector clock examples, I think, are 2 shopping baskets being conflicted. What do you think Amazon does? It puts everything in, so you buy everything. This might be incorrect. It could be, But it doesn't matter. They would rather sell an extra banana, not that Amazon sell bananas, to someone and send an apology letter than have that system unavailable. So that's why these systems exist. If you don't think about conflicts, you'll eventually have a very interesting discussion with your business or your customers, etc., because you will lose data. And the benefit, well, I would happily knock down any node in the Cassandra clusters I run. I would happily scale it up. I was working on a system that was basically doubling users every 6 months at an internet television provider. And we just kept on increasing our Cassandra cluster, right? The ring got bigger, we could store more data, we could support more operations. So on that note, I hope you enjoyed it. This is the first time I've done a talk on Dynamo, so feedback very welcome. Thank you very much for listening. Anyone got any questions before we dive? Yeah. The response times. Mm-hmm. Correct. So the question was, how does the replication affect latency? Like the response time for your application. And it's up to you as an application developer. So I assume that your safe data, you're going to store more than once, right? You're either going to have a read replica on a relational database, you're going to do a backup mechanism, etc. In Dynamo, it's just built in, right? But it's up to you on every single read and write how long you want to wait for that replication. You can actually say to Dynamo-based databases, don't care, and it goes. Or you can say, I want to wait until I'm fully replicated across 7 clusters spread around the world, which will take a long time. It's that trade-off between consistency and latency, and it's up to you on a per query basis. Yeah. Pardon, sorry? Virtually every system I've ever built with systems that are built on top of Dynamo, I've done everything at one, apart from a few transactions where I need specific consistencies like read my own writes. At the moment, we have many, many applications, all using Cassandra. Virtually all of it's one. We have a few quorum read and write, and we have one use case where we actually needed linearizable consistency, and it was the selling of a finite number of vouchers. And the business said, no way, do not even think about selling an extra one. I argued, but yeah, I lost. Yeah. Any more questions? Oh, thank you very much.